All right, so today we have Evyatar Sabag, who will tell us about geometric engineering of 4D n equals to 1 theories from M theory. Take it away.
Okay. Thank you, Julius, and thank you for the invitation to give a talk here in this wonderful Zoominar that you created. So, indeed, I'm going to talk today about the geometric engineering of 4D n equal 1 theories from M theory. And this is based on several works done with Matteo Sacchi, Andreas Braun, and Sakura Sheffer-Namiki, and some ongoing work. So I'll start with the big picture, and basically for me, it's trying to understand and study strongly interacting quantum field theories, describing real-world phenomena. Now, this is obviously a very hard task due to the fact that in most cases, we cannot use perturbation theory. But one or several things we can do to make it easier is, first of all, to add supersymmetry to the mix, and also look at higher dimensions than 4, which makes it easier to use geometric compactification from string theory or M theory to understand these theories. Now, in the last 30 years, there's been a lot of work done about various dimensions and supersymmetries. A lot of work done with 8 supercharges, such as 4D n equal 2, 5D n equal 1, and 6D 1,0. And a few works also done about 4D n equal 1, which is 4 real supercharges. And in these works basically allow to understand in fundamental matter phenomena such as dualities and symmetry enhancement, and also allowed us to study strongly coupled theories using geometry and RG flow, where we can have some strongly interacting geometry, but at some point along the RG flow, we can find maybe a Lagrangian or some weakly coupled description. And basically what I want to discuss today is something towards a 4D n equal 1 classification, basically the very first steps towards it. So I would say my long-term goal would be to have such a classification of 4D n equal 1 SCFTs, and specifically using compactification from M theory on non-compact singular G2 holonomy manifolds. Now, there could be other strategies for this object, but I think this could be one that is very productive. And now, as for G2 holonomy manifolds, these are 7D dimensional manifolds. So as we start from M theory, we can reach 4D. These are Ricci flat, and they're equipped with a closed and co-closed 3 form. And another thing about them is that they break 7/8 of the supersymmetry. So if I start with 32 real supercharges in M theory, I go down to 4D, and I find 4 real supercharges, and this gives me 4D n equal 1. So now I'm going to talk about some known constructions from geometry and also field theory, and start with geometry, specifically a G2 manifold. There are only very trivial 4D n equal 1 SCFTs, which basically hold some free chirals that are known to be engineered using G2 manifolds. And these were done from the math side by Brian and Salomon, and more physics side by Acharya and Witten. In addition, there's in general some semi-methodical ways to construct 4D n equal 1 SCFTs from 61,0 SCFTs by reducing them on Riemann surfaces. And this was done in various works from 2016 to 21 by Kim, Razamat, myself, Vafa, and Tafrir in various papers, not all including all of these authors. But the problem with these works is that these only include some of the 61,0 SCFTs and some of the Riemann surfaces. So it's a very limited constructions, and basically my goal is to try to kind of generalize it and have a more thorough construction that would include the entire family. Now, as for what we are working on right now, we're trying to generate new G2 holonomy manifolds, which correspond to construction of 4D n equal 1 SCFTs from 61,0 SCFTs. So basically trying to translate these same constructions that we had before on a specific set of Riemann surfaces, here basically either flux tubes or tori. Okay, so these are very specific. But hopefully with this more general way of constructing it, we'll be able to use all basically any 61, 0 theory. So in addition, these flux tubular torides, they can be constructed from smaller building blocks denoted as the fundamental flux tubes, which basically correspond to 4D duality domain walls in 5D, which was shown by, again, same authors in several papers. Now, here basically I say we want to construct these 4D duality domains with 5D, and how to relate them basically to the initial 61, zeros. Well, one can compactify 61, zeros on a circle and get 5D KK theories. And in these theories, which can be engineered from M theory on elliptic Calabi-Yau trees, from these we can construct these 4D duality domain walls and basically generate this basic building block that would later help us construct SCFTs. And as I said, hopefully this would allow us to generalize the 60 to 40 construction that was shown before, and to create a G2 manifold geometric construction of 4D n equal 1 SCFTs that would correspond to starting from any 61, 0 SCFT. Okay, so now I'll get to the main focus of this talk, which would be basically just focusing on this very basic building blocks that would later help us generate SCFT. So we would like to generate new G2 holonomy manifold, which geometrize the Gaiotto-Kim 4D n equal 1 duality domain walls of 5D n equal 1 theories, which is basically the which of these very basic building blocks that could allow us constructing 4D n equal 1 CFTs. And just to give a bit of a taste for it, basically, I remind you that M theory placed on Calabi-Yau trees can engineer 5D n equal 1 QFTs, and on G2 manifolds can engineer 4D n equal 1 QFTs. So now, basically, what would be our goal is to take these 5D n equal 1 theories that one can engineer using Calabi-Yau trees, and then translate this construction of duality domain walls to the geometry, such that we'll be able to take these Calabi-Yau trees and construct out of them G2 holonomy manifolds. Okay, are there any questions so far? Okay, good. So now I'll just give slightly more motivation to why we want to look at this. And there's two aspects to it. So first of all, there are many mathematicians that are actually very interested in the G2 holonomy manifolds. And it's quite hard to find non-trivial constructions for these. And here I give just the few examples that are known, and there's very handful constructions that allow to generate these non-trivial G2 holonomy manifolds. And what we plan to do is to use our knowledge from physics, basically, to construct some non-trivial, non-compact G2 holonomy manifold. And in addition, what I'll try to show is that these constructions can help explore G2 codimension 7 singularity resolution, where these codimension 7 singularities are related to chiral matter, which is something that we as physicists are interested in, but it's also interesting from the math point of view. As for the physics, we would like to use these geometric constructions to better understand strongly coupled 4D n equal 1 theories in SCFTs in the same method that was done basically by using Calabi-Yau trees to understand 5D n equal 1 SCFTs. And specifically, what I'll show is that it seems that some of the deformations of our construction of 4D n equal 1 theories from 5D correspond to flowing along the RG flow. So this, again, really reminds us things that were done in the past for 5D n equal 1, where along the RG flow, maybe I can find some weakly coupled regime, and this could help me probe this strongly coupled theory and understand more things about it. Okay. So now I won't keep you waiting. and I'll basically give you the TLDR of this talk. So what are we doing here? So first of all, what is our construction? So pick your favorite 5D n equal 1 SCFT or KK theory. Then you can vary some of the extended Coulomb branch parameters, including mass parameters, along one spatial direction that we would denote as x4. So here in this picture, I show some path basically taken in the extended Keller cone, where here I have phi, which is the vev to some vectors, and m, some mass parameters. And at the origin here, I have the 5D SCFT. Now I can vary these parameters along this line, and in a similar way, each dot on this line would be matched with a dot on the x4 direction. And similarly, I can do it also with 5D KK theories, only here the SCFT point would be a 6D SCFT. And the claim is that this will give, in general, a 4D n equal 1 model. And what we would like to do is to mirror these actions to Calabi-Yau trees, generating basically these 5D n equal 1 theory. And this will give us non-compact G2 manifolds. So now I would like to give some important observations about this construction. So the first important observation is that the resulting theory will be non-trivial if the path in the extended Keller cone crosses duality interfaces. And here I draw them in blue, some duality interfaces as such. Now, how do I define these duality interfaces? Well, I can look at the 5D theory prepotential F, and this prepotential can have, okay, in some cases, a symmetry of the following form, where I can shift phi and m by some function of the masses, as shown here, and get the same prepotential. Okay, so I can look basically with different variables on the same prepotential and get the same prepotential, the same behavior. Now, the interface where these functions basically of the masses vanish is what we call the duality interface. Right, because at this point, basically, I'll have two descriptions that are of the same theory and the same point. And my claim is that this would give non-trivial 4D degrees of freedom. Basically, once you cross these kind of duality interfaces, this would give you non-trivial 4D degrees of freedom.
Is this discrete or continuous symmetry?
Here I would only discuss continuous symmetries, but there is a question about also discussing discrete zero-form symmetries with in general. But I mean, as I say this as a symmetry, I guess, well, maybe this word is not entirely correct. It's basically some transformation of this function that would give you the same function up to a constant.
Okay.
Any more questions so far? So
you will show an example, simplest example.
Yes, I will. So now let's move to the second observation, which is that continuous deformation of the path in the extended Keller cone correspond to marginal, relevant, or irrelevant deformations of the 4D theory. So I can take this path along here, deform it in some way, and basically this would correspond to some marginal, relevant, or irrelevant deformation. Why is this important? Well, some of these deformations might lead us to theories that would be Lagrangian, and this could help us basically study these models. And in addition, such deformations could correspond to resolving codimension 7 singularity of G2 manifolds. Okay, so like we had basically when one studies Calabi-Yau trees, these could have singularities, and resolving them could allow to get you into some IR Lagrangian in 5D. We would hope that one could hope that something similar happens here, and we'll show some examples with where basically one gets a simpler model once doing such a thing.
Just a quick comment or just a quick question on the logic of the geometry. So so you basically are going to come up with these field theory constructions and then conjecture the existence of these G2 manifolds based on this construction on these paths and the Kähler cone?
Yes. So we'll first basically relate ourselves to some known constructions of G2 holonomic manifolds. And then we will build on top of these by some slight deformations of them, so like modding them by Zn, etc. We would get to some models that would not have the mathematical proof of it having G2 structures and everything. But from the physical point of view, we'll have basically some evidence of, well, we know that there's a 4D theory, we know that there's a 4D SCFT, etc. So this would be part of the claim of why these should be G2 manifolds.
Sure, I see. Thanks.
Can I also ask, what is the property of the deformation which makes a difference between relevant, marginal, irrelevant?
So this is still some ongoing research. So I'm not sure basically what's the difference between these deformations, but we're studying currently. But I have some examples where basically one can see that you get marginal deformations in some cases, while in other cases you would expect to get some relevant or irrelevant, depending on which way you go.
I see. Okay, thank you.
Okay, good. Yes, and the last important observation would be that the Kähler cone includes non-trivial loops only for 5D KK theories. Okay, so what do I mean by non-trivial loops? So as you can see here, I kind of drew in a different way the 5D KK theory extended Kähler cone, and this is not an accident. So we define non-trivial loops as one that can only be contracted by going to the SCFT point. Okay, so here, if I assume this is a cone and basically I have this kind of loop, you can see that I can only contract it while going to the SCFT point. And why is this important? Well, the claim is that the non-trivial loops of 5D KK theories are expected to be the cases where the resulting 4D theory would be interacting and flow to a 4D SCFT. So basically, this is part of what we're working on right now, but I still wanted to kind of give a hint for it, as one can think about this X4 direction now as being compact. And if I had such a non-trivial loop, what we expect is to get 4D SCFTs. So we have some field theory and 60 to 4D analysis that was done in this case. So this gives us some reason to think this is true. And basically now we're trying to actually work this out and generate G2 manifolds out of these. Okay, so this is the end of the TLDR. And does anyone have any more questions?
So maybe it's coming in the next slides, in which case you can just tell me to be patient, but can I pick, say, my favorite 5D theory is SU2 with 8 flavors, and you can say something about the 4D n=1 theories that come out in this way? Like, is there an example you can sort of briefly?
So I would, again, in this talk, here I present TLDR to just give you some flavor also to the what's coming up next. But in this talk, I would only discuss domain walls. So we can have a domain wall, and I would actually present this SU2 plus NF flavors example and show you the domain wall and how one can find out basically what are the field theory, 4D field theory degrees of freedom. But I would not show how to get basically the 4D SCFT once one compactifies the X4 direction. So I would only look at some X4 which is some infinite line.
Mhm. I see. Thank you.
Yeah, but this is exactly the example I would talk a lot about, so no worries. Okay, good. So hopefully this sparked some of your interest once I gave you this TLDR, and now you'll be willing to go through some of the more detailed analysis of these kind of things. So let me just outline what I want to talk about next. So first, I'll give some brief background about SCFTs and geometry in 5D and 4D and equal 1, just to give some dictionary on what to expect from both sides. And then I will discuss basically what is the duality domain wall construction that was known before. And once we have these tools, we'll be able to start building G2 manifolds from duality domain walls. And this would be done by a series of examples, where first we start with free hypermultiplet or the conifold, and then we increasingly make the example a bit more complicated by going to actual 5D SCFTs, interacting ones, so the E1 theory, the ENF plus 1 theory, etc. Then finally, I would use these examples to kind of claim that by basically by having this G2 manifold resolved in some way, this corresponds to going along the RG flow. And I'll give an example of what one gets once you stack two of these domain walls of the ENF plus 1 theory. And I'll finalize this with some future directions, which are very interesting to me and hopefully would interest some of you. Okay, good. So now let's start with the background. So 5D and equal 1 SCFTs. So one can engineer these by taking M theory on space X times arc 1, 4, where X is Calabi-Yau3, which has real 6 dimensions, manifold with canonical singularity, and admits a resolution, which we denote by pi, where the canonical singularity corresponds to SCFT. X tilde, which is the Keller cone or the resolution, correspond to going along the Coulomb branch. And one can also have complex deformations, which would correspond to the Higgs branch, but I would not discuss it in this talk.
So you need the existence of resolution because you want to play with the parameter space?
Yes, for the 5D theory. Yeah, I want Calabi-Yau3s that I can resolve.
Okay.
Yeah, because this entire construction would be built on going along the Coulomb branch and varying the parameters there in some sense.
Okay.
Okay. So what are the properties of the 5D theory? Well, non-abelian symmetry would correspond to codimension 2, and here all the dimensions are complex. Codimension 2 singularity, where G effective to the -2 correspond to the volume of the underlying curve. And if this curve is non-compact, meaning it has an infinite volume, this would imply that the symmetry is global, and otherwise this would be a gauge symmetry. One can take this non-abelian symmetry and resolve it. So basically go to the Coulomb branch and find just the abelian part of it. And this is done by introducing divisors, which are complex surfaces. In addition, we can have charged matter, such as hypermultiplets, which are codimension 3 codimension 3 singularities intersecting codimension 2 singularities. And specifically, I can think of a massive hypermultiplet as resolution by introducing some complex curve, and the mass of the hypermultiplet would correspond to the volume of the underlying curve. Now, in this specific talk, I would have some simple constructions, and this would focus on toric Calabi-Yau3s. Now, these models are simpler in some sense, and we can describe them by having toric diagrams that have a bunch of nice properties that allow us to actually see things in a clearer way. So these diagrams are composed of the following. So they have some points which correspond to divisors. So you can think about the points as corresponding to the symmetry, where external points correspond to non-compact divisors, so global symmetry, and internal ones correspond to compact divisors, so these are related to the gate symmetry. In addition, we have lines which correspond to complex curves. And I forgot to mention that in this example, we look at the conifold. So this is the Calabi-Yau3 that allow us to engineer a free hypermultiplet in 5D. Now, as for the complex curve here, basically resolving this space by adding this complex curve correspond to giving a mass to the hypermultiplet, while the unresolved space, like we had here, correspond to having a hypermultiplet with 0 mass. And I can do it in 2 different ways. I can resolve it like this and this. And this would correspond to like changing the sign of the mass of the hypermultiplet. One can think about full or partial resolutions. So this means if I fully triangulate the space or not fully triangulate it. And these are all or some internal non-intersecting lines being placed. So here, this is basically a full resolution, and we can also have a full resolution like this. Now, the nice thing about these toric diagrams is that they allow me, in a simple way, to get the algebraic description of the geometry. So these divisors that appear here have coordinates. And using these coordinates, I can find a relation between these divisors. Once I have this relation, I can translate it to an algebraic equation where I have a complex parameter associated with each divisor, which are these zi. And this equation would now be equal to the volume of the curve that I use to resolve the space. So in this case, if I resolve it with this red curve here, C24, T would correspond to the volume of C24. While if I resolve it with the blue one, C13, T would correspond to minus the volume of C13. And all of this is modeled by U1. Okay, so I won't get into the details of how we can see this. This is why this is the algebraic description, but just accept it as so. And basically, we get one equation and mod U1 for each curve in the full resolution. So here in my full resolution, I only have one curve, internal one. So this is described by one equation. So next I'll go to 4D and for 1 SCFTs in geometry. So similarly to what we had before, you can take M theory on X times R1, 3. Only this time X is a G2 holonomy or real 7D singular cone. And here we would find that non-abelian symmetries correspond to codimension 4, and now all the dimensions would be real because this is not a Calabi-Yau manifold. So non-abelian symmetries correspond to codimension 4 singularities, where GFFT to the -2 correspond to the volume of the underlying 3 cycle. And you can think about it as having C2 mod gamma fibered on top of a 3 cycle, as giving me this non-abelian symmetry. Chiral matter corresponds to codimension 7 singularities, and here you see why this codimension 7 singularity pops out as something important. It has to do with chiral matter, which, if we want to describe real-world physics, we really want to include in our theories. And charged chiral matter basically is this 7D singularity intersecting with a codimension 4 singularity. In addition, since this is 4D and equal 1, I have superpotential terms, and these come out as 3 cycles intersecting several codimension 7 singularities, where these 3 cycles have no singularity fiber on top of them. Any questions so far? Good. Now, finally, let's go to the duality domain wall construction. So, what do we have here? This construction is suggested by Gaiotto-Kim in 2015. And here you basically start from 5D n equal 1 SCFT. And just to illustrate it, I'll give an example of the rank 1 E1 SCFT, which it's important to note that its flavor symmetry is SO3 in D. Now, we can flow towards the IR and find a Lagrangian description for this. And we choose to do it in two different ways with a domain wall in between. Now, here, for this example, we get a pure SU2 gauge theory, which has an instantonic flavor symmetry of U1. Now, in both sides, I have U1, but the point is that this U1 fits inside this SO3 in a different manner, where specifically U11 is actually minus U12. And what we find is that on the domain wall, we have some degrees of freedom, which gives us a bifundamental between the two SU2s coming from the two sides. Okay, so this is a bifundamental chiral, just to emphasize. And in general, we can have the two IR flavor symmetries embedded inside GUV in a different way and get such domain walls. Okay, and obviously this could be generalized to other examples, such as the ENF plus 1, etc. So this is the basics of this construction, and that's what we'll use from now to generate our G2 manifolds. So are there any questions before we start with the actual construction? Okay, good. So first we start with a very simple construction using the 5D free hypermultiplet, or the Calabi-Yau 3 node, the conifold, where the domain wall is constructed by varying a 5D free hypermass such that it passes through 0. And this was suggested by Chan, Ganor, and Crow in 2001. So this is a known construction, okay? This is not something new. But we want to phrase it in terms of the domain wall we're using, so we can use it later in a more complicated way. So this is constructed by placing M theory on the resolved conifold. And we find the following picture, where now let's decompose it. So first of all, we can see that we have these squares here. So these are the toric diagrams for the conifold. And we can see that on the left, I resolve it with this red curve here, the C24, while on the right, I resolve it with C13. This corresponds to having a positive mass on the left and a negative mass on the right, which means that in the middle, this mass goes to 0. And what we can do now is we can basically show how these curves change along the x4 direction. And remember, these are complex curves, so I can draw them as two cycles. So, and these two cycles correspond again to the volume of them corresponds to the mass of the hypermultiplet. And we can see that we get this kind of picture here, where I have a non-compact 3-cycle on the left, a non-compact 3-cycle on the right. And in the middle, I get this singular point. This kind of a transition is called a flop transition, where I go from one resolution like this to another. And this gives me a codimension 7 singularity, which indicates that there could be some chiral matter localized here. And again, I go back to the equation we just saw a few moments ago, which describes the conifold. And what I can see that I can choose this parameter t over here to be equal to the mass. And for example, I can take its profile to be minus x4, such that I get positive mass on the left and negative mass on the right. Now, like I said, this model was well known beforehand, and it was analyzed also from a field theory point of view and from the geometry point of view. And both of them basically agree and find that this codimension 7 singularity have a single free chiral localized on the domain wall. Now, the important thing to show here is basically what's the mathematical justification for this being a G2, and that's what we'll do now. So what I can do is look at this equation, and I see that I can basically choose any parameters Z1, Z2, Z3, Z4, and I would always find a T that would satisfy this equation. So I can rewrite this equation basically as being C4 mod U1. Now I can rewrite things with a new coordinate R, where basically all the squares of the I equals to R squared, and R is some positive real number. So this means that basically this part here is an S7 for every R. S7 mod U1 gives me a CP3, and then I have the real positive line. So this gives me a real cone over CP3. And this was shown by Brian Salmon that there is a conical metric on CP3 with a singular limit of a smooth asymptotically conical G2 holonomy manifold. Okay. So this just comes to show that there is some mathematical base for this. And in this case, it was really shown that one can write a metric for this space and have all the properties required for it to be a G2 holonomy manifold. Okay. So this gives us basically a strong mathematical base to build on top our physical construction. One more thing that we can do with this very simple example, but it's still very nice and illustrates some things that I want to illustrate, is that we can stack domain walls. So what does it mean? I can have this mass being positive here, then going to negative and back to positive. So this would give me some singular point here, another singular point here. So I have one free chiral and another free chiral. And in the middle, I would carve out some 3-cycle in between them. That would mean that we have a superpotential coupling, given basically these two chirals, a mass term in our superpotential. Now this can be done using replacing T by x4 squared minus A, just to get this kind of profile. And one nice thing that you can see is now that once I reduce A, basically these 2 points would come closer and closer together. And once I get to A be 0, these massive chirals get integrated out. And once I go for negative A's, I'm left with a trivial domain wall, meaning there are no 4D degrees of freedom here in the middle, right? Because I just have this one phase of M larger than 0. So this is some basic way of relating the RG flow to resolving codimension 7 singularities in a very trivial way, but still it shows basically what can be done with these kind of constructions. Okay. Any questions about this construction, which everything would be built on top of it from now on? Okay, good. So now we get to a bit more complicated construction, and we work on the E1 5D SCFT. So in this case, in the IR, we have pure SU2, and the domain wall is constructed by varying the instant on mass M0 such that it passes through 0. So very similar to what we had before. But now we can look at the prepotential. So this is, Ami, what you asked for before, like kind of an example of what would be the transformation. So I can think about a transformation now that takes M0 here in this prepotential to minus M0, and think what would be the transformation that phi undergoes in order to get the same prepotential up to constant terms. So here I didn't actually explicitly specify it, but there is a transformation where phi goes to basically phi plus or plus or minus some m0 up to some fraction. I just don't remember right now. But the point is that there should be also a transformation for phi. So now that I want to describe this domain wall, well, on one side I have this instanton mass going from positive to negative. But in addition, this phi would go from being 0 on one side to being non-vanishing on the other side. And now I can look at the toric diagram for this model. So here I get the following square only tilted, and I also have this compact divisor to this internal point here, which I call S. But besides that, everything seems very similar, right? I have this resolution here with the red curve. I do a flop transition and go to this resolution here with the blue curve. And I have here this non-compact 3-cycle carved out, and also on the other side. But the only difference is that in this case, I have a Z2 singularity on top of it, which would mean that there's an SU2 symmetry on the left and an SU2 symmetry on the right, as we expect basically from this model that in the IR is pure SU2. And in the middle, again, I'll have a codimension 7 singularity. And what one can find is that we get the following quiver, where again, we have the SU2 from the left, SU2 from the right, bifundamental in the middle. And in addition, I would not get into details, but one can also show that there's a singlet field here that is coupled through this superpotential term. But basically here, looking at it from geometrical point of view, I didn't do much. All I did is take the free hyper case or the conifold case and mod it out by Z2, which is geometrically what we get here. So this is just a generalization of the free hypergeometry modded by Z2. But as for the 40 degrees of freedom, we get something a bit more complicated and a bit more interesting. Okay. Now, for the last step, we'll crank it up even more, make it a bit more complicated by basically having this SU2 plus an additional hypers. And we can draw it out in the following way, where again, we have this square like we saw before of the E1, but now there is an additional triangle going on here with several divisors, which would correspond to having NF flavors. And in our case, we choose all their masses to be equal. So we get from this part here an SUNF symmetry in addition, global symmetry. Now, I would like to go back to the Keller cone and see what happens with the path we go through in this Keller cone. Where in the last few examples, this Keller cone was very simple, so I didn't bother showing this. But here, this kind of makes it more interesting. So like I said, I choose all the hypermasses to be equal. So this is just one direction here. I have just one Coulomb parameter, phi. And in addition, I also fix some combination of the instanton mass and the hypermasses to be constant. And this gives me basically some scale that I can write down in this diagram. Now, what one can find is that there are two duality interfaces for this theory. One where all the hypermasses are MC/8, and another one where the masses and the phi are equal. So this is this line here. And the path we choose to go through is this red one going through here. And the claim is that whenever you go through a duality interface, you get a flop transition. So, which means that we will get some non-trivial 40 degrees of freedom. So now we can write down our geometry by basically taking all the curves we have here and fibering them along the x4 direction. So we get this non-compact three-cycle, the red one and the blue one, just like we had before. In addition, we have some three-cycle carved out by this C14 curve here, which we'll discuss in a minute. And in addition, we have a non-compact three-cycle in green here, which comes for the SUNF symmetry that we have from the hypers being of the same mass. And this would give us an SUNF symmetry. So this basically have a ZNF singularity on top. Okay, now let's decompose it. So for starts, we have basically the volume here of C24, which corresponds to the G effective -2. And similarly in blue here, we have the volume of C13, which corresponds to the same thing. Next, we have the hypermasses, where here I distinguish between the parametric mass that I take here and the physical mass that one sees, where this curve in this diagram corresponds to the physical mass, but the physical mass is just the parametric mass minus phi in absolute value. And now we can see basically why we get this duality interface here, because once basically the masses are equal to phi, this physical mass goes to 0, and we get this singular point in our geometry. And now we can see that we get several flop transitions. So we have the flop transition that we had before between these two regions, but we also have the ones here and here, where we basically have a flop transition similar to the one we had with the conifold, where just having some hypermasses moving from positive mass to negative or vice versa. And now we can interpret this diagram and get a 4D n=1 quiver. So we have the quiver that we had before with the two SU2s and the bifundamental. But in addition, we also have here codimension 7 singularity between this SU2 and the SUNF. So this gives me this field. And similarly, on the other side, this gives me this field. And one more important feature here is that we get this, basically this superpotential term for the triangle. And this comes out from having the three-cycle here intersecting these three codimension 7 singularities. Okay, so this basically exemplifies how we can write down the geometry in some sense. This could also be algebraically written down, but I didn't want to clutter this. And we can interpret it and find out what is the field theory quiver description. And what we get is that we reproduce all the expected 4D theory properties that we want from the geometry. Now, this sort of construction could be also extended for other 5D SCFTs, but this was just one example. Okay. And okay, so this is up to here with the construction. Are there any questions? Okay. Good. Now the final part would be relating G2 manifold resolution to RG. So here, what I do, I basically stack the same domain wall we had just a minute ago. I stack two of these together. So I have here one triangle like we had before, another one like we had before. But now we see that here in the middle, I get a gauge symmetry instead of a global symmetry. And this is due to the fact that now this three-cycle is closed off and it's compact. Okay, unlike it was before, but the red parts here are not compact.
So your construction is always Lagrangian, or there's no restriction?
So no, not necessarily always Lagrangian. It depends on the path you choose in the Keller cone. So here specifically, we chose some path along the Keller cone, which does give us a Lagrangian. And my hope is that given any path on the Keller cone, you can always deform it into some path that would give you a Lagrangian, which would basically correspond to resolving this geometry. But we have not shown this yet.
And how do you expect to read so those theories are conformal, what you're getting with these quivers?
So
not necessarily.
Well, I wouldn't say this is basically a bunch of free fields. So I wouldn't call it an interesting conformal SCFT. But these are just building blocks to what comes next. Like I said, when we want to compactify the X4 direction and actually get 4D and 1 SCFT.
I see. And so you would have some kind of a conformal manifold in those cases?
Mm-hmm.
And what kind of physical data do you expect to extract from the construction?
So my hope is that by using some smart way of deforming our path along the extended Keller cone, I'd be able to extract quiver for hopefully any theory by just having this basically having the path going through these duality interfaces in such a way that there's only simple chiral multiplets in between them and nothing more singular in some sense. Because in general, I can have something very, very singular that would include like a huge theory in between, and this would just look like a codimension 7 singularity. But hopefully by deforming it in some way, I'll be able to extract what are the actual Lagrangians.
Okay, thank you.
Okay, so now basically that we stack two of these domain walls, we would like to see some nice, interesting properties. So first of all, we can see that we have here, of course, now this drawing is less pretty than the one before, but still, believe me that this is a 3-cycle that goes between two codimension 7 singularities. And this gives me basically a mass term for these two chirals here, R1 and L2. I also have these two triangles, which gives me the cubic superpotential term for these two triangles here. And I can also draw the Keller cone path as shown here. So this is the same Keller cone path we had before, going on the red line up to this point. But then basically what we do is we come back along the same line with the purple line here and go back to the same starting point that we had, okay, which would give me this kind of construction. And now the claim is that reducing A corresponds to flowing towards the IR. So again, I reduce these intersection points here, A, and this would slowly make this geometry go towards the IR and actually less singular. So first thing I can do is basically integrate out this massive chiral. This is done by taking these 2 points and getting closer such that this purple piece is gone. And that's what we find. And now basically these two orange pieces are joined together, so we get a quartic superpotential for this entire thing. As for the Keller cone path, we see that now we do not cross this duality interface here, which means we lost some of our chiral map. Okay. Next, what we can do is we reduce A even further. We see here from the field theory point of view, we have an SU2 with 4 flavors. So this could be, we can move to a cyberdual frame where this SU2 disappears and we're only left with a bunch of fields. And that's what we get, basically, once we reduce it even further. And what we're left with is now just 2 chirals with a mass term. And as you can see here in this Keller cone path, we also now don't cross this blue line here. the final step is integrating out these massive chirals. And in this case, what we come back to is basically a 5D theory of SE2 plus NF flavors with some mass profile for these flavors. Okay, so now we're basically left with no 4D degrees of freedom, and the 4D theory became true. So this is basically further relates the RG flow to resolving Cotta-Match 7 singularities. So here we had more interesting stuff than just integrating out massive chirals. We also had this cyber dual frame. And this should also show how deformation of the path in the color cone should be related also to resolving Cotta-Match singularities. Questions so far before I finish?
Yes, can I ask a question, please?
Yeah.
So I'm slightly confused here because so the parameters that you have in the killer cone are real. On the other hand, in the superpotential, you would expect complex parameters. So how does the correspondence work?
So as for you mean the actual coefficient in the superpotential?
Yes.
Yes. Yeah, so indeed, in this case, these parameters should somehow correspond to the volumes of some 3 cycles that we see. But yeah, I would not know how to tell you how to see them as complex, or in what sense we can have parameters that are complex. Yeah, it seems like the volume is only a real number.
Thanks.
Yeah, I could just emphasize that this is a generic problem. What Stefano points out is a generic problem because the 4D n equals 1 theories has a very clear complex structure. There is a very clear notion of a chiral field, and when you deal with the real geometry, it's not clear how to extract a complex structure out of that. So it's going to be an issue all along. Yeah. And I'm not aware of any good solutions.
Okay, thank you for the comment.
Yeah.
Okay, so I'm almost out of time, so let me finish with some future direction. So first of all, like I already said, we have some ongoing work about having 4D n equal 1 SCFTs, where we basically would like to compactify this X4 direction. We would like to choose 5D KK theory and consider a non-contractible loop in the extended killer cone. In addition, we would like this loop to pass through a duality interface in order to have some 40 degrees of freedom, as we've seen so far. And we expect that continuous deformations of the loop will also pass through duality interfaces in order to get an interacting SCFT, right? Because like we seen in the former example, we don't want to have some loop in such a way that I can contract it and basically not pass through a duality interface, because in that case, my 40 degrees of freedom would be trivial. There's also several questions that are very interesting to me for future directions. So one is, can one find Lagrangians for many 4D n equal 1 field theories that have a construction from 5D SCFTs or KK theories, but have no known Lagrangian? Okay, so there are many other, let's say 61,0 models, which you can do this kind of procedure that was known before, but no one can find a Lagrangian along the RG flow of these. And yeah, and this could perhaps be done by deforming the path in the color cone to resolve codimension 7 singularities. So maybe this deformation along the path in the color cone could allow us to find this. And also some another continuing along this line, can one basically fully understand how to resolve codimension 7 singularities by looking at various such examples? A different direction, which is more along going towards such 4D n equal 1 classification or something along these lines is, can we also geometrize constructions from 61,0 reduced on higher genus surfaces, right? So far, I just discussed these cubes or domain walls and maybe a torus, but what happens once I want to go to higher genus or some other Riemann surfaces with more punctures? And there are some known ways from 60 to 40 to take like a torus and add punctures to it. And the question is, can we look at these structures, geometrize them, and maybe generalize them? And finally, can similar constructions be used to generate spin 7 manifolds, which, if we start from M theory, can allow to engineer 3D n equal 1 field theories and SCFTs. So this would get us even further along with less supersymmetry. And if we could still somehow find geometric tools to help us study this, this could allow us to understand maybe more field theory phenomena or strongly coupled theories that we didn't have access until now. Okay, that's it, and thank you.
All right, let's thank Evyatar for this nice talk. Do we have more questions? Okay, so we had plenty of questions, of course, during the talk. I would say let's then move straightforwardly to the after party, and I'll stop the recording. You can thank Evyatar one more time.
Okay, cool. Thank you, Julius.
Thank you.